So somewhere in Los Angeles right now, sitting behind this bulletproof exhibition glass, there is a rock.
A very, very small rock.
Right, a rock smaller than a Tic Tac, actually. And it completely defies the laws of statistics. I mean, in 4.5 billion years of churning, violent geological history, our planet has only ever managed to make exactly one of these.
Just one.
Yeah, just one. So today we are basically tearing apart the Earth's chemistry lab to figure out why. Welcome to a new deep dive. We are exploring the extreme limits of planetary geology and really hunting for the rarest physical objects on Earth.
It's a journey that forces us to completely rethink what the ground beneath our feet actually is,
Right.
Like we look at a mountain, we just assume permanence.
Sure, it's just rock.
Exactly. But if you zoom in, if you look at the atomic forces at play, the Earth is not a static piece of bedrock. It is a terrifyingly dynamic, high-pressure chemical factory. And to understand it, we are pulling data today from the Mineralogical Magazine, the American Mineralogist, various geological databases from ESESCO, and the curatorial archives of the Natural History Museum of Los Angeles County.
And our mission today is to shortcut your way to understanding that chemical factory. We are going to use two impossibly rare minerals to explore the exact, impossible conditions required to create singular geological masterpieces.
And we're going to see that the Earth basically has two very different methods for cooking up these anomalies. One involves a deep earth pressure cooker running for millions of years.
Right.
And the other is a toxic, searing volcanic vent that creates rarities out of thin air in an instant.
It's wild. Okay, so let's start with the deep earth pressure cooker. And I want you to really picture this, because we aren't starting with some abstract chemical equation. We're starting with that physical object I mentioned earlier.
The one in the museum.
Exactly. It's a transparent reddish-orange gemstone that weighs just 1.61 carats.
Which is roughly 0.3 grams. I mean, for visual scale, the measurements are 5.8 by 4.58 by 3 millimeters.
Wow.
Yeah, you could literally lose this in the lint at the bottom of your pocket. It's less than a quarter of an inch long.
So the mineral is called Kyawthuite. And setting the scene of how this single object came to be known to humanity, it feels like the setup to an incredibly high-stakes lottery.
Oh, absolutely.
So the year is 2010. We are in Myanmar, specifically in a stream bed near Chomgi village.
And this specific region is historically famous for sapphire hunting. You have local prospectors out there constantly sifting through the river gravel. They're washing away the mud, looking for the telltale flash of blue sapphires, maybe some red spinels.
And we actually don't know who pulls this tiny, rough, tawny-hued stone out of the muck.
Right.
And they don't recognize it as a high-value sapphire,
Yeah.
probably because it's orange and, microscopic, so they
Yeah.
just toss it into a parcel of rough stones destined for the local Chongi market.
Which is a bustling, chaotic environment. Rough stones are changing hands constantly. Buyers are examining muddy pebbles under harsh sunlight, just trying to guess what might be hiding inside.
Enter Dr. Kyaw Thu. He's a Burmese mineralogist and gemologist with a PhD from Yangon University. He's walking through this market, and he spots this tiny speck.
Yeah.
Initially, he thought it might be scheelite, which is a tungsten ore, or maybe a piece of topaz, but he didn't just walk past it. Something made him stop.
And that is the power of expert intuition. Like when you've looked at tens of thousands of stones, your brain subconsciously recognizes anomalies in light refraction or crystal habit before you can even articulate what's wrong.
Right.
So Dr. Kyaw Thu buys the rough stone,
Right?
and then he makes a wildly risky decision.
Yeah, he decides to facet it, which means he decides to cut and polish it into a gemstone. And why is that so risky?
Because if it's an unknown mineral, you have literally no idea how brittle it is. You don't know its cleavage planes, those internal weak points where the crystal structure naturally wants to split. He could have put it against the polishing wheel and watched the only specimen on Earth just shatter into worthless dust.
But he didn't. He successfully facets it. And as he's working the stone, examining how the light bends through it, he realizes this behaves like absolutely nothing he has ever seen.
Right.
It's not scheelite, it's not topaz. So he sends this faceted stone to the Gemological Institute of America, the GIA laboratory in Bangkok.
And the GIA doesn't just look at it with a magnifying glass. They subject it to a battery of intense chemical and crystallographic tests. And what they discovered was completely unprecedented.
Yeah.
The chemical formula and the specific arrangement of the atoms had just never been observed in nature before. By 2015, the International Mineralogical Association confirmed it as a brand new mineral.
Okay, let's unpack this. Finding the stone is like looking for a needle in a haystack, except you don't even know what a needle looks like, and there's literally only one needle in the entire world.
The statistical improbability is staggering. Just think of the chain of events here.
Right.
A piece of rock erodes out of a mountain, survives tumbling down a river without being ground into sand, gets picked up by a miner looking for something else entirely, ends up at a busy market, and happens to catch the eye of one of the few people on the planet with the academic training to realize it isn't just a piece of dirty quartz.
Okay, I completely hear you on the improbable journey, but I have a major stickler point here.
Okay.
If this stone was found tumbled in a stream bed, surrounded by river rocks and gravel, how could we possibly state with absolute certainty that it is the only one?
That's a fair question.
Like, if it broke off a larger deposit up in the mountains, couldn't the rest of it have just washed away millions of years ago? Or couldn't there be 100 more sitting in the mud of that exact stream, completely ignored by miners who only get paid for blue sapphires?
That is the exact right question to ask. But when the International Mineralogical Association, the IMA, which maintains the global database of all 6,000 plus known minerals, when they designate something as the only known specimen, they aren't just taking a wild guess.
So how do they prove a negative? How do they prove there aren't more out there?
Well, they don't prove a negative, but they rely on an exhaustive global dragnet. Myanmar is one of the most heavily mined and intensely studied gemological regions on Earth.
Right.
Since 2010, the entire global gemological community has been on high alert. Every mineralogist knows the chemical signature of Kyawthuite. Everyone knows its optical properties.
Okay.
Yet, in well over a decade of continuous industrial-scale sifting of that region, not a single additional microscopic fragment has been found.
So it's heavily vetted by just a complete lack of further discovery. But wait, if they've never found another one, how do they know some brilliant chemist didn't just synthesize this in a lab and accidentally drop it in the river?
Because the Earth leaves a fingerprint that a lab cannot replicate. When the GIA analyzed the Kyawthuite crystal, they found specific shear stress markers inside it.
Shear stress markers.
Yeah, there are microscopic hollow tube-shaped inclusions called en-echelon veins.
En-echelon veins. Okay, break that down for me. What is happening physically to the rock to create that?
Think of a pristine deck of playing cards. If you press your hands flat on the top and bottom of the deck and push your hands in opposite directions, the cards don't just slide smoothly.
Right.
They fan out, creating these angled parallel gaps between the individual cards. That sliding, tearing force is shear stress.
So the rock was essentially acting like that deck of cards.
Exactly. Deep underground, as the crystal was slowly growing, it was subjected to immense, violent tectonic forces that tried to tear it apart.
Wow.
This tectonic shear stress created microscopic step-like fractures inside the crystal structure itself. A synthetic crystal grown in a calm, controlled, temperature-regulated laboratory beaker would be structurally perfect.
Because it hasn't been crushed by a mountain.
Right. It wouldn't have the scars of a violent tectonic birth. Those en-echelon veins prove it was forged deep inside the Earth.
That paints an incredibly violent picture of what's going on underground. And I think if we want to figure out why Dr. Kyaw Thu found Kyawthuite exactly where he did, we have to look closely at that violence.
We do.
We need to zoom out from the stone itself and look at the valley that created it. And that is the Mogok stone tract.
Mogok is the absolute epicenter of extreme planetary chemistry. If you are a geologist, Mogok is holy ground. It's an environment where the normal rules of rock formation are just permanently dialed up to their absolute maximum intensity.
Geographically, Mogok is a valley in northern Myanmar. It sits about 3,500 feet above sea level, roughly 50 miles west of the Irrawaddy River. And visually, the descriptions we have are stunning.
It's gorgeous.
It's this lush landscape. The hills are covered in shrubs, dotted with small villages. And rising out of the rock outcroppings everywhere are these incredibly well-tended Buddhist shrines, pagodas covered in gold leaf that just reach skyward out of the jungle.
It's deeply beautiful, but its real legend lies underground. For centuries, Mogok has been known globally as Ruby Land. Yeah, the historical accounts are almost comical. The abundance of precious gems was so ridiculous that locals were said to find flawless rubies just glinting in the grass of their backyards after a heavy rain washed the dirt away.
And it isn't just ancient history. There are highway signs there today that literally read, "Welcome to Ruby Land."
Yeah.
There are roughly 1,000 working mines and diggings operating in that valley right now.
It's incredible.
It produces what are widely considered the world's finest rubies, sapphires, spunols, and peridot.
But here is the geological paradox. Gems, by their very definition, are rare. They don't typically form in massive, mountain-sized ore deposits the way iron or copper do.
Right.
You don't just find a solid vein of ruby a mile long. Gems require very localized, highly unstable, very specific chemical anomalies to form.
So why is this one specific valley so absurdly packed with them?
To answer that, we have to rewind the clock 50 million years. The Indian subcontinent wasn't always attached to Asia. It was essentially an island, drifting rapidly northward across the ancient ocean. And then it collided with the Asian continental plate.
I was reading about this collision, and it's honestly hard to wrap your head around the physics. It wasn't just a bump. It was a slow-motion, catastrophic kinetic impact.
A massive impact.
Millions of square miles of solid rock slamming into each other, buckling the Earth's crust upward to create the entire Himalayan mountain range.
The sheer amount of kinetic energy transferred in that crash is almost incalculable. And all that kinetic energy had to go somewhere. Much of it converted into localized environments of unimaginable heat and crushing pressure deep underground.
And this is the key to Mogok's weirdness. It wasn't just subjected to one type of geologic force. The data reveals 3 entirely distinct extreme environments operating in this single region at the exact same time.
Right.
I want to try to map these out because it's fascinating. The first environment is called a pegmatite. From what I understand, this is basically a magma chamber that just refuses to cool down.
That's a great way to put it. Imagine a localized pocket of magma pushing its way up from the mantle into the crust. Normally, magma cools relatively quickly into standard igneous rock, like granite.
Okay.
But a pegmatite is rich in water and volatile elements, which actually lowers its freezing point. So it stays liquid for millions of years, cooling incredibly slowly.
I was trying to visualize this, and the best analogy I could come up with is making a reduction sauce on a stove.
But why is that?
You start with a big pot of liquid, and as it simmers over a long time, the water boils away, and all the intense flavors, the rare elements, get highly concentrated in the remaining liquid. Because it cools so slowly, the atomic building blocks have an enormous amount of time to find each other and stack up perfectly, which allows the crystals to grow to massive sizes.
That reduction sauce analogy is spot on. As the common elements crystallize out first, the remaining liquid becomes a highly concentrated soup of the weird, heavy, exotic elements that didn't fit into the normal rocks.
Like what?
Things like lithium, beryllium, or in the case of Kyawthuite, titanium, niobium, tungsten, and uranium.
And we know Kyawthuite formed in one of these pegmatite reduction sauces because chemical analysis of the stone revealed trace amounts of those exact heavy elements.
Exactly.
Okay, so that's the first environment. The second force running wild in Mogok is metamorphism.
This one is a direct result of the tectonic crash. Imagine a vast deposit of limestone. This used to be an ancient seabed made of the crushed shells of microscopic marine life.
Right.
When India slammed into Asia, that seabed was buried deep underground, subjected to millions of years of intense heat and crushing pressure from the mountains folding directly on top of it.
The pressure essentially cooks the limestone. It physically compresses and reorganizes the rock until it transforms entirely into marble.
Yes.
And during that violent transformation, if the chemical impurities in the rock are just, right, say a little bit of chromium gets trapped, it crystallizes into a gem. That's the mechanism that birthed the famous Mogok rubies.
Precisely. And then, layered on top of the pegmatite magma pockets and the crushing metamorphism, you have the third environment, hydrothermal fluids.
This one sounds like an insane plumbing system. We are talking about highly pressurized, superheated, watery fluids circulating through deep cracks and fissures in the Earth's crust, roughly 15 to 25 million years ago.
Yeah, and these aren't just hot puddles. Because the water is under such immense pressure, it can get much hotter than its normal boiling point without turning into steam.
Okay.
This superheated water acts as a highly aggressive solvent. It dissolves rare minerals out of the surrounding rock, carries those elemental building blocks along the fault lines, and then, as the temperature or pressure eventually drops, the dissolved elements precipitate out. They reform as entirely new, pure crystals clinging to the walls of the cracks.
So if we look at the big picture of the Mogok Valley, You have the slow-cooling exotic magma pockets, you have the crushing mountain-building metamorphism,
Yeah.
and you have this superheated chemical plumbing system. And they aren't separated by hundreds of miles. They are all physically overlapping and interacting in this one localized spot. It's literally a geological blender running for 50 million years.
It is the ultimate laboratory. Dr. George Harlow from the American Museum of Natural History has spent time analyzing Mogok, and he described it as a jaw-dropping experience.
Mm.
There is quite literally nowhere else on the planet with such an overlapping, diverse suite of mineral-forming environments.
But here's what I find so compelling. Even in the ultimate geological laboratory, with every possible force acting upon the rocks, producing something like Kyawthuite still requires a chemical recipe so bafflingly specific that it almost defies logic.
The recipe is the true mystery. Mogok provided the oven, sure, but the ingredients themselves dictate why only one stone exists. We have a look closely at its highly unusual chemical formula.
The empirical formula for Kyawthuite is Bi3 plus Sb5 plus O4. Translated into plain English, it is bismuth, antimony, just bismuth, antimony, and oxygen. And structurally, it forms in a monoclinic crystal system.
Right, and for anyone who hasn't taken a crystallography class recently, crystal systems are just the 3D geometric shapes that atoms form when they stack together.
Right.
A simple cubic system looks like a perfectly square box. Monoclinic basically means the box has been skewed. It's a rectangular prism where one of the angles isn't 90 degrees. It looks like a slanted box.
The records also note it has an adamantine luster. That means it sparkles brilliantly, refracting light almost like a diamond does. And if you were to scrape it across a piece of unglazed porcelain, it would leave a pure white streak. But I want to spend some time on the ingredients themselves, starting with the heaviest element in the mix, bismuth. Chemical symbol Bi, atomic number 83.
Bismuth is a fascinating element because it defies so many of our standard expectations for heavy metals.
I was reading the database files on this and I was immediately thrown off. I assumed, because Kyawthuite is the rarest stone on Earth, that bismuth must be some mythically scarce element that barely exists.
No, it's not.
Right. The data says bismuth is actually comparable in abundance to silver in the Earth's crust. It's not impossibly rare at all.
That's true. It is relatively abundant. But we don't usually dig a dedicated bismuth mine. In nature, bismuth strongly prefers to hang out with lead, zinc, or tin. Commercially, we harvest it as a byproduct of refining those other metals.
I looked into how that refining actually works, and the process is wild. We get a lot of our bismuth from what's called anode sludge during electrochemical refining.
Oh, yes. The sludge.
Basically, they take an impure block of copper or lead, drop it into a chemical bath, and run an electric current through it. The pure copper dissolves and travels across the bath to stick to the other side.
Right.
But the impurities in that block, things like silver, gold, and our friend bismuth, don't make the jump. They literally just fall to the bottom of the tank as this highly valuable toxic mud called anode sludge.
And humans have been scraping up that sludge and utilizing bismuth for a surprisingly long time. The earliest recorded use goes all the way back to the mid-1400s.
Really?
Yeah, they discovered that if you alloyed bismuth with other metals, it was perfect for casting the metal type used in the very first printing presses.
But they didn't know what it actually was back then, right?
Right. Early scientists, like the German scholar Georgius Agricola, studied it and just assumed it was a weird variant of tin or lead. It wasn't until 1753 that a French chemist named Claude-François Geoffroy definitively proved it was its own distinct chemical element.
Physically, if you look at elemental bismuth, it is striking. It is a brittle white metal, but it has this distinct, beautiful pinkish iridescence to it. But the absolute weirdest thing about bismuth and the physical anomaly that blew my mind is what happens when it freezes.
The thermodynamic anomaly, yes.
Almost every single metal in the universe shrinks when it turns from a liquid to a solid. The atoms lose kinetic energy, they slow down, and they pack tightly together, making the solid denser than the liquid.
Exactly.
But bismuth expands by about 3% when it solidifies.
It is one of the very few elements that behaves like water turning into ice. When liquid bismuth cools, the specific angles of its atomic bonds force the atoms to lock into an open, rigid lattice structure that actually takes up more physical volume than when they were freely sloshing around as a liquid.
Because of that unique property, we use it today in fusible alloys metals that melt at very specific low temperatures. If you look at the fire sprinklers in the ceiling of an office building, the little metal trigger holding the water back is often a bismuth alloy designed to melt the second the air gets too hot.
And perhaps the most counterintuitive thing about bismuth, Look at where it sits on the periodic table. It is sandwiched right next to lead, thallium, and polonium.
Right.
Some of the most highly toxic radioactive heavy metals known to science.
Yeah.
Yet elemental bismuth is virtually non-toxic to humans.
We literally drink it to settle our stomachs. Pepto-Bismol. The bismuth is right there in the name. So you have this weird, heavy, pinkish, expanding, non-toxic metal, and in Kyawthuite, it is bonded with antimony. Now, because bismuth is so incredibly heavy, it gives Kyawthuite a shocking density. The measured density of this microscopic gem is 8.256 grams per cubic centimeter.
To contextualize that number, pure water is exactly 1 gram per cubic centimeter. Kyawthuite is more than 8 times heavier than an equal volume of water.
That's insane.
It is literally double the density of a ruby. If you held that tiny 1.61 carat stone in the palm of your hand, your brain would instantly reject it. It would feel impossibly artificially heavy for its size.
Okay, here is where things get genuinely confusing for me, and I want to push back on the entire premise of this stone's rarity. Wait, you just agreed that bismuth is as common as silver, and antimony, while less common, isn't some mythological unicorn element either. Furthermore, I read that scientists can, and frequently do, make synthetic bismuth antimonate in a laboratory.
They do.
The chemistry works. It's a totally viable bond. So if the ingredients are relatively common, and the chemical bond is stable enough to make in a lab, why on earth is there only one natural specimen? Why is the Earth so terrible at making this naturally?
It is a brilliant contradiction. And to solve it, we have to look past the ingredient list and look at the architectural blueprint.
Okay.
It's not just about having bismuth, antimony, and oxygen in the same room. It is about the excruciatingly precise way they are forced to hold hands.
Are you talking about the crystal structure?
Yes. The crystallographic analysis of Kyawthuite is intensely complex. At the atomic level, the antimony atoms, specifically antimony 5+ ions, bond with oxygen atoms to form what are called octahedra. These are essentially 8-sided geometric shapes.
Okay, I'm picturing an 8-sided die from a board game.
Good. Now, these antimony-oxygen octahedra share corners with each other, linking up to form flat, continuous, checkerboard-like sheets. Imagine a microscopic tile floor made of antimony and oxygen.
Okay, I have the checkerboard sheets. Where does the heavy bismuth fit in?
The bismuth atoms are located above and below the open squares in those checkerboard sheets. They form chemical bonds stretching down to the oxygen atoms in the sheets, linking the separate flat sheets together into a 3D structural framework. But here is the critical failure point. The bismuth atom in this specific structure is forced into what chemists call a lopsided 8 coordination.
Lopsided? That doesn't sound like a stable, happy atomic bond. What makes it lopsided?
It happens because bismuth possesses a feature called stereoactive lone electron pairs. Let me break that down. Bismuth has 2 valence electrons that refuse to participate in any chemical bond.
Oh.
They just orbit the atom in a pair.
Yeah.
But because electrons carry a negative charge, they physically repel the other negatively charged electrons that are trying to form the bonds with oxygen.
So this rogue pair of electrons acts like a physical wedge, taking up space and pushing all the other bonds out of alignment.
Exactly. It shoves the whole structure to one side. The bismuth atom is forced into this awkward, highly asymmetrical position just to hold the framework together.
Okay, I think I see the problem. When a scientist makes this in a pristine laboratory, they control the exact heat, the exact pressure, the absolute purity of the chemicals, and the precise rate of cooling.
Yes.
They basically coddle the atoms until they agree to hold hands awkwardly.
But the Earth does not coddle anything. In the Mogok Valley, you don't just have pure bismuth and antimony. You have massive amounts of silicon, iron, calcium, magnesium, dozens of common elements constantly swirling around in that 50-million-year-old pegmatite blender.
And those common elements probably form nice, neat, perfectly symmetrical bonds without any lopsided lone electron pairs getting in the way.
Exactly. Nature favors the path of least resistance. For Kyawthuite to form, a specific pocket of magma had to be extremely rich in bismuth and antimony, yet miraculously devoid of any other elements that would eagerly bond with oxygen to form more stable minerals.
Wow.
Then, that incredibly pure, weird pocket of magma had to be subjected to the exact temperature, the exact pressure, and the exact microcooling rate required to force these atoms into this highly unstable checkerboard structure.
So if the magma was hotter by even a few degrees, or if there was even a trace amount of silicon present?
The chemical reaction would have pivoted instantly, and it would have formed a completely mundane common rock instead. The fact that the Earth managed to isolate these ingredients and align these atoms perfectly, naturally, without any chemical contamination, is a statistical anomaly so vast it borders on the miraculous.
That is a profound testament to the random, chaotic power of deep Earth pressure over millions of years. But as staggering as the Mogok Valley is, tectonic pressure deep underground is only one way the Earth cooks up the impossible.
That's right.
Our planet has a second, completely different method for creating rarities, and this one doesn't happen miles underground over millennia. It happens out in the open air in some of the most violent, toxic environments on the surface of the globe.
We are leaving the deep Earth pressure cooker behind, and we are stepping into the searing exhalations of an active volcano. We are going to look at a mineral called Fingerite.
If Kyawthuite is the beautiful, bright orange gemstone born of ancient mountain building, Fingerite is its dark, menacing cousin. It is classified as a pauper vanadate. Its chemical formula is Cu1102VO46.
Quite the mouthful.
Yeah, and it was discovered in a location that frankly sounds like the final level of a video game. The summit crater fumaroles of the Izalco volcano in El Salvador.
A fumarole is essentially an open wound on the side of a volcano. It is a vent that violently exhales superheated, sulfurous, toxic volcanic gases directly from the magma chamber below.
Okay.
The Izalco volcano itself is a massive basaltic composite cone, and it's been continuously, intermittently active since the 1770s. It is an incredibly harsh, unforgiving environment.
And Fingerite absolutely looks the part. It is pitch black. It is entirely opaque. It has a dull metallic luster. And if you scratch it against a testing plate, it leaves a dark reddish-brown streak, very similar to hematite. It doesn't form nice big gemstones. It occurs as these tiny microscopic crystals, intimately intergrown with other bizarre toxic minerals like the nardite and euchlorine.
The story of its discovery is fascinating because it really highlights how incredibly difficult the fundamental science of mineralogy actually is. Fingerite was officially identified in these volcanic vents in 1963. They named it in honor of Dr. Larry W. Finger, who is a renowned scientist at the Geophysical Laboratory and contributed massively to our understanding of crystal chemistry. But the attempt to classify this exact chemical compound actually started years earlier, and it started with a massive scientific error.
I loved reading about this mistake. In 1958, two scientists named Brucey and Molinari were doing laboratory experiments, trying to figure out what happens when you mix copper oxide and vanadium pentoxide.
Yeah.
They published a paper claiming they had identified a stable phase with a neat, clean ratio of 4 parts copper to 1 part vanadium. They declared the formula was CO4V209.
It looked great on paper. But when later scientists like Fleury in the 1960s tried to replicate this experiment and synthesize this specific 4-to-1 ratio in the lab, they completely failed. The chemistry physically didn't work. The resulting compound was unstable.
So what did Brucey and Molinari do wrong?
They didn't actually analyze the physical chemical products of their reaction. They relied entirely on X-ray diffraction.
Let me stop you there, because X-ray diffraction sounds incredibly complex. How does shining X-rays at a rock tell you what's inside it?
It's essentially a way to see the invisible atomic architecture. Think of throwing 2 pebbles into a calm pond.
Okay.
When the ripples hit each other, they interact. Sometimes they amplify each other, sometimes they cancel each other out, creating an interference pattern. When we shoot a beam of X-rays at a crystal, the X-ray waves hit the orderly rows of atoms inside the crystal and bounce off. As those waves bounce back, they interact just like the ripples in the pond.
And because different minerals have differently spaced atoms, the ripples bounce back in unique patterns.
Precisely. By looking at the mathematical pattern of the returning waves, the diffraction peaks, we can calculate exactly how far apart the atoms are, which tells us what the structure is. It acts like a mathematical fingerprint.
Right.
Brucey and Molinari looked at the diffraction fingerprint, saw something that vaguely fit their math, and made a heavily educated guess that it was a 4-to-1 ratio.
But they guessed wrong. It wasn't until scientists got their hands on actual natural Fingerite crystals scraped from the El Salvador volcano and hit them with advanced electron microprobes, which actually analyzed the exact chemical composition point by point that they realized the mistake.
Yeah, it wasn't even close.
The ratio wasn't a clean 4-to-1. It was an incredibly messy 3.33-to-1. The actual formula, Ca11V6026, is immensely complex and weird.
What's truly captivating here is the stark contrast in how these two impossible minerals, Kyawthuite and Fingerite, actually formed. We established that Kyawthuite grew slowly inside a liquid pegmatite magma over millions of years.
Right.
Fingerite did not form from magma. Fingerite did not form from a liquid at all. Fingerite is what geologists call a sublimate.
A sublimate. In physics, sublimation is when a solid turns directly into a gas, or a gas turns directly into a solid, completely skipping the liquid phase in between. Dry ice does this. It turns straight from solid carbon dioxide into fog.
Exactly. Inside the Y fumarole of the Izalco volcano, the environment is chaotic. You have superheated, highly acidic volcanic gases rushing up from the magma chamber. Because it's so violently hot, heavy metals like copper and vanadium are literally vaporized. They exist as toxic gases.
So you have gaseous copies swirling around in the dark.
Yes. As these vaporized gases rush up the vent toward the surface, they hit the outer sulfate zone of the fumarole. Suddenly, the temperature drops slightly. Specifically, it drops to between 100 and 200 degrees Celsius.
Okay.
In that exact thermal window, the kinetic energy of the gas drops just enough that the copper and vanadium atoms are forced to bond with oxygen. But because of the specific pressure and temperature ratio of the vent, they cannot condense into a liquid droplet.
So what happens?
The atoms essentially lock hands in midair and deposit directly onto the rock wall as a solid jet black crystal lattice. Fingerite condenses directly from a toxic gas into a solid rock.
It is quite literally born out of thin air, violent toxic volcanic air.
Born out of thin air, but only if the temperature gradient is flawlessly perfect. If that rock wall is 250 degrees, the copper stays a gas and vents into the atmosphere.
Wow.
If the rock wall is 50 degrees, different elements condense out instead. It has to hit the exact thermal sweet spot for Fingerite to precipitate.
So let's look at the contrast between these two rarities. Fingerite crystallizes in a triclinic system. We talked about monoclinic being a slanted box. Triclinic is the most asymmetrical, chaotic crystal shape geometrically possible.
It's a mess.
It's like a cardboard box that has been completely crushed, no equal sides, no right angles, just total asymmetry. It's black, opaque, and born of toxic volcanic gas in an instant. Meanwhile, Kyawthuite is monoclinic, vibrant orange, totally transparent, and born of immense deep earth pressure over millennia.
They are polar opposites in every phase of their genesis, yet they share a profound, almost terrifying level of rarity. We know Kyawthuite exists as a single 1.61 carat stone. Fingerite is barely more abundant. Decades of searching that volcano have yielded only milligram amounts of Fingerite, which are now carefully guarded in the vaults of the Smithsonian Institution and the Geophysical Laboratory.
It really makes you pause and think, and I want to put this directly to you, the listener. What stands out to you? When you picture the sheer catastrophic force required to make something truly unique in the universe, is it the deep, crushing, slow-motion weight of whole continents collapsing into each other that captures your imagination?
Or is it the searing, violent, toxic heat of a volcanic vent, creating black crystals out of thin air that feels more alien to you?
Both of these extremes are operating right here on Earth, underneath us, creating things we can barely comprehend.
It speaks to the vastness of geologic time and the infinite, delicate variables of chemistry, but it also raises a cultural question. Once humans actually manage to find these impossibly rare items, once we pry the single orange gem out of a riverbed in Myanmar or scrape the black flakes off the toxic vents of a Central American volcano, what happens to them? What is their ultimate fate in our society?
Well, they undergo a massive transformation. They transition from being purely geological anomalies, weird chemical freaks of nature, to becoming cultural treasures. They become highly curated artifacts of human curiosity. And that brings us perfectly to the current home of the sole Kyawthuite specimen.
It resides at the Natural History Museum of Los Angeles County, the NHM.
The NHM is showcasing Kyawthuite as the crown jewel of a major exhibition called Unearthed Raw Beauty. According to the museum's curatorial data, this exhibition runs from December 2025 all the way through April 2027.
Right.
And its entire focus is dedicated to showcasing the rarest, most spectacular mineral specimens ever discovered, explicitly displayed in their natural uncut forms.
Placing Kyawthuite in this specific exhibition is a brilliant curatorial choice. Because when you're looking at a 1.61 carat orange speck, you desperately need context.
Exactly.
You need to understand the colossal scale of what the Earth is capable of manufacturing to truly appreciate how special that tiny speck is. The other items in this exhibition provide that necessary scale.
I was looking through the list of other geological marvels they are displaying, and it paints an incredible picture of the Earth's capabilities. For instance, they have a specimen called the chrysanthemum stone.
Oh, that one is beautiful.
This is a massive boulder of rock weighing over 900 pounds. And naturally growing through this dark, black, muddy shale rock are brilliant white crystals of a mineral called celestine. But They didn't just grow in random blocks.
No, the formation process is stunning.
How does it actually form to look like a flower?
The celestine, which is strontium sulfate, precipitates out of water that gets trapped in the muddy shale before the mud fully hardens into solid rock. It starts at a single nucleation point in the mud, and as the crystal grows, it pushes the soft black mud outward in all directions.
Oh, wow.
Because of the way celestine crystallizes, it forms these long, radiating blades. The end result looks perfectly, like massive white chrysanthemum flowers blooming inside pitch-black stone.
It looks like something a sculptor spent months carving, but it is entirely an unthinking product of chemical precipitation. Then, the exhibition features red amylite from Alberta, Canada. Amylite is fascinating because it's essentially a fossil.
Right.
It is the fossilized shell from an extinct marine mollusk called an ammonite, which looked like a squid living in a coiled shell. But under the right tectonic pressure, the mineral aragonite inside the shell alters, creating a gemstone that exhibits intense iridescence.
The optical physics of amylite are incredible. It changes color depending entirely on the viewer's perspective. You shift your head an inch, and the color morphs from deep red to flashing green.
Why does it do that? It's not actually changing color, right?
Right. It's called light diffraction. During fossilization, the immense pressure of the Earth compresses the aragonite into millions of microscopic stacked translucent plates. When ambient light enters the stone, it bounces off these different microscopic layers.
Just like the X-rays.
Exactly. As the light waves bounce back out, they interfere with each other, just like the X-rays we talked about earlier. If you change your viewing angle, you change the physical distance the light has to travel through the plates. That changes which light waves cancel out and which amplify, instantly changing the color your eye perceives.
It's millions of years of compression resulting in a naturally occurring optical illusion. The NHM also highlights enormous amethyst geodes from the Artigas department in Uruguay. We're talking caverns of rock formed roughly 80 million years ago, lined with deep purple quartz.
Yeah.
But what makes the ones in the exhibition, which are literally named Oscar and Window, so special, is that they experienced a secondary geological event. After the purple quartz crystals finished forming, a completely different batch of mineral-rich water flooded the geode, and glittering white calcite crystals grew perfectly suspended in the center of the purple voids.
And since the museum is located in Los Angeles, they naturally feature California's own geological treasures. They have a massive specimen of Kyawthuite, a deep blue barium titanium silicate that is the official state gemstone.
Right.
And they have a natural gold flame, which is the state mineral. It is a piece of raw, unrefined gold that naturally precipitated out of hydrothermal fluids into the exact shape of a leaping fire.
Surrounding the microscopic Kyawthuite with these massive, visually stunning giants, 900-pound stone flowers, giant purple geodes, leaping gold flames might seem counterintuitive at first, but it actually drives the point home perfectly. The Earth can effortlessly make a 900-pound flower out of rock. It can make massive caverns of purple crystal. But with all its power and all its time, it could only manage to make 1/3 of a gram of Kyawthuite.
So why do we do this? Why do we spend millions of dollars to extract these rocks from the dirt, polish them, insure them, and put them on velvet pedestals behind bulletproof glass with little spotlights on them?
I think it's our human attempt to capture and understand a scale of reality that is otherwise terrifyingly large. The human brain cannot comprehend 50 million years. We cannot emotionally comprehend the weight of the Himalayan mountain range crushing a continent.
No, it's too much.
But we can look at a tiny orange stone or a black flake scrape off a volcano and say, this right here, this is the result. It takes the immense, abstract, terrifying scale of planetary time and chemistry and makes it tangible. You can stand in a museum and look it right in the eye.
Exhibitions like Unearthed serve a truly vital intellectual purpose. They bridge the massive gap between hard, uncompromising science, things like atomic structures, stereochemically active lone pairs, sublimation thermodynamics, and tectonic shear stress and pure instinctual aesthetic appreciation. We humans are drawn to the beauty first.
Always.
The sparkle, the color, the impossible shapes, but that beauty acts as a Trojan horse for deeper understanding.
It tricks us into learning geology.
Exactly. It reminds us that minerals aren't just dead, boring rocks sitting in dark caves. They are the active, operating foundation of our entire technological world. The exact same chemical rules of electron bonding that formed that singular Kyawthuite gem are what allow the purified silicon in our electronics to process data. The same calcium of precipitation rules that form the geodes allow our very bones to support our weight. It is all part of the same grand, ongoing chemical experiment.
It is deeply, deeply humbling when you zoom out like that.
Okay, let's pull all of these threads together and recap the incredible journey we've taken today. We started in the muddy, chaotic gemstone markets of Myanmar, where the sharp eye and expert intuition of Dr. Kyaw Thu saved the only known piece of Kyawthuite from disappearing into obscurity forever.
We traced the origins of that single 1.61 carat orange gem back 50 million years to the violent slow-motion tectonic crash of the Indian subcontinent into Asia.
Right.
We explored the unique, highly localized, overlapping geological blender of the Mogok stone tract. We saw how slow-cooling pegmatite reduction sauces, crushing metamorphism, and superheated hydrothermal plumbing combined to create the ultimate mineral oven.
We zoomed all the way into the atomic level, examining how seemingly common ingredients like bismuth and antimony were forced by impossible statistical odds into a highly unstable, lopsided crystal structure.
Yeah.
And then we threw all those deep earth rules out the window and traveled to the summit of the El Salvadoran volcano of Izalco. We saw how superheated toxic copper and vanadium gases bypassed the liquid state entirely, condensing in midair to solidify into milligrams of the jet black rarity known as Fingerite.
Two completely different minerals, formed by completely opposite extremes of the Earth's capabilities, yet both end up as testaments to the staggering rarity of perfect environmental conditions. And finally, we saw how human beings framed these discoveries, placing them in museums not just as shiny curiosities, but as vital, tangible links connecting us to the deep, slow, massive forces of the planet we live on.
Because the truth is, the earth beneath your feet right now is not static bedrock. It is a continuously operating chemical factory. The ground is literally alive with heat, with immense pressure, and with the slow, inexorable march of geologic time. Every single rock you kick on the sidewalk is a frozen moment of intense chemical history.
It makes you wonder, as we sit here right now, how many other only known specimens are currently washing down an unexplored riverbed in the Amazon, or quietly crystallizing in the toxic vent of a deep ocean trench, just waiting for the right pair of eyes to notice them.
That is a brilliant point. The factory is still running. And that leads me to one final thought for you to take away today. We've spent this entire deep dive looking down deep into the crust of our own little planet. We've seen that Earth, with all its incredibly complex, chaotic, overlapping geological systems and its 4.5 billion years of history, has managed to produce exactly one tiny crystal of Kyawthuite.
Yeah.
One.
Yeah.
So, I want you to look up. Think about the infinite expanse of the universe. Think about the billions upon billions of exoplanets currently orbiting distant stars. What completely unique, impossible, one-of-a-kind minerals are sitting right now on the surface of alien worlds? Minerals forged by volcanoes spewing liquid methane or crushed by atmospheres of super-dense neon gas, just waiting out there in the dark for us to find them.
The parameters for chemistry out there are completely untethered from our earthly rules. The murky waters of discovery truly are endless.
Thank you for joining us on this deep dive into the extremes of geology. Keep looking closely at the world around you because you never really know what kind of impossible history is hiding inside a tiny stone.